everyone and welcome. In today's video, we will be introducing you to noise analysis in vision. But first of all, it is worth mentioning that in vision, both time and frequency domain noise analysis are possible. And you can visit our documentation for any complementary information that's not mentioned in these tutorial videos. In today's video, we're going to focus just on the frequency domain noise analysis using noise figure representation. Through noise figure representation, we can visualize how much noise was introduced to the system by the device or by a specific series of devices. In fact, NF analysis is done using a probe in our software that's called CW-NF probe, and the calculations behind the probe are in continuous or CW mode and are done as follows. First, we turn off all internal noise sources and calculate how the device operates with a large signal. This step looks at the steady state condition. After that, once the steady state response is calculated, the circuit is linearized, which means that the circuit's behavior is approximated by a straight line, linear approximation, making it easier to predict small changes like noise. Afterwards, the noise is added back as a small perturbation or disturbance to the steady state solution, and the output noise is calculated based on this. In the calculation, the conversion matrix is used in the analysis, and it represents how sensitive the device's current is to the changes in voltage across different frequencies. And in simpler terms, it helps map how noise at the input affects noise at the output. And by using a matrix, the software can analyze noise across different frequencies and harmonics, but for this specific case, only the fundamental frequency is analyzed. In a later time in this video, we will be analyzing the noise representation of this whole schematic, but first, we will be extracting the behavioral model of each component of the schematic and analyzing its behavior. Let us start by extracting the model of the LNA. To do that, we go to our device modeler application and then choose the LNA model and create a new device. I'm going to extract a model of LNA BSP, and I'm gonna name it LNA tutorial. Then click on OK to create the device. The next step is inserting the measurement file or the circuit simulation file. For me, it's gonna be a measurement file. This one. When it comes to the maximum number of pollen residues, I'm gonna start with 10 and then increase it in order to have more precision when the model follows the data. If I want more precision, I'm gonna increase it. If the precision with 10 poles is sufficient for me, I'm gonna leave it. When it comes to including noise in vision, if we have a linear component like the low pass filter, I'm gonna be analyzing afterwards. There's no special thing to do. You just have to go to the block representing the linear component, then activate the noise, and also activate it in the source and the simulation control, as well as in the impedance model. There's an underlying formula of thermal noise that's taken into consideration in the calculation. But on the other hand, if we have an active nonlinear component like the LNA I'm using here, the thermal noise formula is not sufficient. And in this case, measuring noise figure of the component and adding it to the model is necessary. So here I'm adding the noise factor file. I'm gonna look for it here. I'm adding it, then I'm extracting the model. Okay, now that I have the model, I can visualize my results. Here, see the important results and see the accuracy of the model. If it's sufficient for me, then I carry on and go to the extraction of the rest of the models. If not, I come and increase the number of fallen residues. There's another curve that we can visualize in addition to the S parameters, that is the noise figure curve that we can visualize here. We are then going to extract the model of the low pass filter. It's gonna be SNP model. So I'm gonna name it low pass filter tutorial. And click on OK. Then, just like the other model, I'm gonna choose the measurement file, and I have to add the number of ports. It's S2P, and the desired answer would be baseband, and then I'm gonna extract. Then I close and visualize again the results. And here we can see that S12 and S21 are quite identical because the filter is reciprocal. For the third component, we are not extracting a model, but using the S parameter files directly in the schematic, because the measurements for the DSA were done for different attenuations. So for each attenuation, we have a file of S parameter measurements, and that is why instead of extracting the model, we are using an SNP block, and instead of vision file format, we using a parameterized touchstone format, because the parameterized S parameter allows to read the available files here for certain attenuations and then interpolate between those attenuations. So how are we going to use this parameterized S parameter option? The first thing we are going to do is go and create a folder. Mine is called DSA SNP, and regroup all the measurement files in this folder. Here I have my folders for all the attenuations. Then I'm gonna create, in the same directory as the folder, I'm gonna create a data file that contains these parameters. The first parameter is the number of ports. I have components with 2 ports, so it's gonna be 2 for me. The second parameter is the number of frequencies for whom the measurements were done. I have 800 frequency. Then the number of parameters controlling the files. Here my parameter is the attenuation, so I have 1 parameter, so it's going to be 1. And then the number of values that the parameter takes, I have 8 values, and I come and write explicitly the values that the parameter takes. And of course I come and write the file list of all the files used by the block. And here we can see that starting from the directory of the data file, I'm gonna add the directory of the folder, then the name of the file. So the directory to the file always starts from the directory of the data file. Now that we have put in place the measurement files and the data file, we are going to the parameterized S parameter. We are gonna, after of course sliding the block from the linear distributed palette, we double click on the block, and then we choose the loop in order to select the component, which is the SA, and then the data file, which is the data file that we configured earlier, and the data type is S parameters, and the data format would be parameterized touchstone format, and the interpolation method would be cubic spline, and the control mode would be a switch. The variable we're gonna use to switch between the files would be, for example, I'm gonna call it control, then click on OK. The next step is I'm gonna add a simulation control and a variable. This variable would contain the control parameter that I added here in the SNP block. The next step to simulate and analyze this block, I forgot to change the name. I'm gonna change it. It's DSA. We're adding a source. It's gonna be a CW simulation. Then a frequency source. And then we're adding impedance at the output of the DSA with 15 ohm resistance. This is what would be in a classical simulation, but we're gonna add probes to this simulation in order to visualize and analyze the performance of the DSA. So I'm gonna add probes, W meter probes to the input and output also. I'm changing it from voltage and current to incident reflected power wave. I'm gonna do the same thing to the output probe, and then connect here. I'm gonna also add a CW NF probe because obviously the goal is to do noise analysis, and we are gonna add it to. We have to take the incident power and not the output directly. Of course, we're having a scope, which is a waveform for me, and I'm gonna name it the variable I'm gonna visualize. I'm gonna name it NF, and I'm gonna visualize it in a magnitude and phase. We can add to that probe to visualize the gain also. Why not? We need a waveform too. This time it's gain. We have to mention that when we have brackets, it means that the input or the output is complex, but when we don't have them, it means that they are real. So here I should change the input of the waveform to real signal in order to not have an error. And for the gain, I'm gonna connect it. And lastly, we are activating the noise in the chart by clicking on the resistance and activating the noise, and then validating by clicking on OK. The next thing we are doing is choosing the type of simulation. It's gonna be a CW simulation with sweep nested analysis. Then we are gonna go to the noise. We're doing a frequency domain noise analysis. And if you would like to change the temperature, you can go ahead and change it. Then click on OK. We're then going to set the source, the CW source. I'm gonna put -13, the amplitude. And then we shouldn't forget, of course, to add the noise because it's a noise simulation. And click on OK. And then for the frequency, I'm not gonna put a set value, but a variable that I'm gonna sweep in the variable block, and then click on OK. We shouldn't also forget to activate the noise in the DSA and click on OK. Then in order to do the sweep, we have to insert the variables in the variable block. I'm gonna start by the control variable. And the nominal value, I'm gonna put 0. And for this variable, it's gonna be a list. It's the same list that was indicated here. I can just copy it. but I shouldn't forget to add a punctuation between the values. It's the syntax for the block. We are then clicking on OK, then OK again. Here we have set the variable control, but we have to set also the frequency variable. So I'm gonna add a new variable. I'm gonna name it frec, the same name I've put here in the frequency source. I'm gonna put nominal value of 2 gigahertz. And for this variable, it's not gonna be a list, but a range, because I'm gonna do lots of points. 2 gigahertz to 18 gigahertz and 100 points. The next step is to simulate the schematic. We'll click on run. We can see that the simulation is pretty fast. Then we visualize the results of the simulation. Here we have different curves for the different attenuations. We can choose to analyze the first curve for the first attenuation, and here we can see that the noise increases when we increase the frequency, and we can also see the difference when we add attenuation. We can also see that the value of the noise figure increases as well. We can also visualize the gain for the same attenuation, and we can see that with the increase of the noise figure, we have a decrease of gain. And that's it for the DSA. We are going to do the same thing, the same analysis for the LNA. That's why I'm going to copy the schematic, copy and paste it in the schematic of the LNA. But I'm going to change the device here. I'm going to delete it and go to the device model results, LNA tutorial, and slide the component here. Easy. If we double click on the block, we can see clearly that the path to the model is inserted directly. We're gonna activate the noise. Click on OK. And the other thing we're gonna change is we're gonna remove this variable and click on OK. Then we're gonna simulate. When we visualize the results, we can see that the noise figure is decreasing for the LNA with the frequency, and we can compare it to the noise figure plot that we saw when we extracted the model. We can see that they are similar, with less measurement noise here in the plot in the simulation. We can also visualize the gain of the LNA. We are then going to analyze the last component, which is the low pass filter. I'm going to take the same schematic and copy it and paste it on the schematic of the low pass filter. I'm going to change the device. I'm going to go to the device model results and then to SNP and low pass filter tutorial. And I'm gonna directly slide model. If we double click, of course, we have the file, and we're gonna activate the noise and click on OK. Then simulate and visualize the results. Here's the NF for the low pass filter 2 and also the gain. We can clearly visualize that for the low pass filter, neither the noise or the gain are as high as those of the LNA. Now that we have analyzed and simulated each component alone, we are going to simulate the system as a whole. We added the components, the source, and all the probes we've seen earlier, and we're doing a sweep of the control and frequency, and also a frequency domain noise analysis, of course. We're going to simulate the system. We can see that the simulation is pretty fast, 0.58 seconds for the simulation, and we can visualize the results here. Here's the NF for one attenuation. We can see that it's pretty similar, if not similar to that of the LNA, because it was the highest. Also, we can visualize the gain for the system, which is a bit lower than that of the LNA by itself, due to the contribution of the other elements.